So let's start off with a vector space V, which is finite dimensional. And let's remember what that means. First of all, you're a vector space, and the finite dimensional means there is some finite spanning set. Now, let's fix a basis. So remember what a basis is. A basis is some subset, I'll call it big B, the collection of elements, B1, ... we'll say to Bn. This is a subset of V, a basis. So what does basis mean? Well, it means two things. It means it's a spanning set. So just to remind us here, this means that the span of B1 to Bn is all of V. And in addition to that, it's linearly independent. So a basis is a spanning set which is also linearly independent. So if this is the case, the size of a basis is called the dimension. Any two bases automatically have the same size. So this is a well-defined concept. So the dimension is the size of any basis. So the aim of this lecture, we're going to use this basis, use B, to kind of think about kind of V in a more concrete way. So what do I mean by that? Well, this whole theory is super duper abstract. I mean, we're talking about a vector space, which is some set equipped with some structure. It's very hard to kind of wrap your head around what that means. We have various examples of vector spaces, and some of them are really kind of tangible. For example, Rn is a very tangible vector space. Elements of that are columns of numbers. We can really understand the sum and the scalar multiplication. It's something we've thought about a lot. So the basic idea is to use a basis to think about V in a more tangible way. So here's a really important fact for you. So what is a basis? So it's spanning and it's linearly independent. So each x in V, so any vector, can be written in the form, well, I can write it as a linear combination of the basis vectors in a unique way. So what do I mean by that? Well, first of all, the can. You can be written as a linear combination precisely because the span of B1 to Bn is equal to V. So this is because of the spanning. The more interesting part is the uniqueness. So it turns out the linear independence means that if you were to try to express one vector x as a linear combination in two different ways, so perhaps with different lambda1 to different lambda n, that's impossible. The linear independence forces any linear combination expression for x to be unique. So this is the linear independence. So this isn't too hard to show. It's done in the textbook. In the interest of time, I'm not going to do it, but it's a really crucial fact. So first of all, it can be written as a linear combination because of the spanning, and it's unique because of linear independence. So what does this mean? Well, to any vector x in V, I can associate a collection of numbers now. I can associate the numbers x1 to xn. So let's kind of make this a bit more formal. So definition. So the coordinate vector of x relative to the basis B is just, well, it's the column vector given by lambda1 to lambda n. Lambda n in Rn, where x is equal to lambda1 b1 sum ... to lambda n bn. So every single vector x in V can be associated with a column vector in Rn, and this is the way you do it. So this is kind of a really cool idea. It allows us to think about elements of V, this kind of abstract vector space, in really concrete terms. If, for example, I tell you what the coordinate vector of x is relative to b, I can always reconstruct x, because if I know what the basis is, I just write down this linear combination, and that's what x is. So this gives me a really kind of nice way to think about things in a concrete fashion. So let's introduce some notation for this. I mean, I want to write something where we take into account what the basis is. We're trying to write coordinates in, but we write this. So the vector x, written in coordinates b, or b coordinates, whatever you want to call them, this is lambda 1 to lambda n. So this is a really concrete way of thinking about a vector. So this is really useful when I have a really super abstract vector space. I mean, if we're talking about, I don't know, solutions of some sort of homogeneous differential equation where there's no kind of obvious way of thinking about it concretely. If you make a choice of basis, then you can convert everything to coordinates. So let me do a few examples, because this is a difficult idea. So the first one is, I mean, let's just make sure this is a sensible concept. I mean, if I take V is equal to Rn itself, so the thing about Rn is it comes with this privileged basis. So let's have B is equal to the standard basis. So if the standard basis is being used, well, what's the thing about the standard basis? Well, notice that if I take any vector, x1 to xn, if I'm going to write this as a linear combination of the standard basis, it's brilliant. I just have to take the coordinates themselves. This is x1 e1, some x2 e2, dot dot dot, some xn e to the n. So what does that mean? Well, let's look at this definition. If I take a vector and I want to write it in b coordinates, I have to write it as a linear combination of the vectors and then just take the weights if you want. So immediately I can see that if I do this with the standard basis, I get exactly the usual representation of a vector back at me. So x1 to xn, written with respect to the standard basis, is just the same thing again. And it's very important that this b here is the standard basis. We'll see in a second, if I don't choose the standard basis, that's not going to be true. It's kind of going to be strange, it's going to be difficult to wrap our heads around, but to begin with, Rn, the standard basis, is just the usual representation of a vector. So this is great. Okay, so in Rn, the standard basis coordinates are just the usual coordinate representation of a vector. So the real power of this comes when we're thinking about vector spaces that are a bit more general. So let's take, I don't know, polynomials. So let's do V is equal to Pnr. So this is degree at most n polynomials. And let's choose a basis B is equal to, let me think, let's do kind of the most natural one we could choose. 1x, x squared up to xn. This is frequently called the standard basis. For degree n polynomials. The reason being is it's the most natural one. I mean, if I take a polynomial, virtually by definition, it's a linear combination of these. So this is a really elegant way to think about polynomials, and it's something intuitively you may have encountered before. I mean, if I take the polynomial a0 plus a1x plus dot 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 up to a n, x to the n, and I ask myself, what is that in b coordinates? Well, it's exactly what you think it is. It's just the coordinate vector a0, a1, dot dot dot, down to an. And notice, this isn't in Rn. It's easy to get a bit confused here. There are n plus 1 basis elements. So this guy is sitting inside Rn plus 1. So this is a really good way to think about polynomials. I can convert them using the standard basis of polynomials into column vectors with n plus 1 components. Okay, so this is really I think there's nothing too special with this. It's so natural to think about this kind of coordinate representation. What is more difficult is the idea of choosing bases which are not quite so obvious. So let's do the following example. Let's take V as equal to R2, so that's the plane, and I'm going to mess with us a bit. Instead of taking the standard basis, let's take the basis, let's say 1, 1, 0, sorry, what am I saying, 1, 1, and let's do 2, 1. Now, why is that a basis? Well, it's a linearly independent set of size 2. It's also spanning because R2 is two-dimensional, so it's definitely a basis. I mean, they're linearly independent because they're going in different directions. Here's a question for you. So what is 5, 3 written in B coordinates? It's an interesting question. So, I mean, you'd think, well, it's just 5, 3 back again. But remember, 5, 3 would only be what we get back if I choose the standard basis. The standard basis up here means that when I represent things, it's just exactly the same coordinates back. But you see, I'm not choosing the standard basis. I'm choosing 1, 1 and 2, 1. So this seems like a crazy thing to do. Why would you ever do it? I promise you there are going to be good reasons to think about coordinates in different bases. We'll start to see them next week. But first of all, how do we work this out? Well, we need to know what? We need to know what 5, 3 is as a linear combination of the basis. That's how we work out the coordinates. We need to express 5, 3 as a linear combination of 1, 1 and 2, 1. So how do I do that? Well, I need to use some sort of augmented matrix. So let's do 1, 1 and 2, 1, 5, 3. So solving this linear system is the same thing as expressing 5, 3 as a linear combination of 1, 1 and 2, 1. So if we do this, we'll go through the usual procedure. I'm going to get 1, 2, 0, minus 1. Is it 5, minus 2? And we go again. So let's put it in reduced echelon form. 1, 0, 0, 1. I think I get 1, 2 here. Okay, so now if I solve this, what do I get? I would get x1 is equal to 1 and x2 is equal to 2. So what does this correspond to? This corresponds to the fact that 5, 3 as a linear combination of 1, 1 and 2, 1 is 1 times 1, 1 plus 2 times 2, 1. So let's wrap our heads around this. This is, if you were using the B notation, this would be lambda 1, B1 plus lambda 2, B2. So I'm thinking about up here, this is B1 and this is B2 from my previous notation. So what does that tell you? Well, this tells me that the vector 5, 3 written in B coordinates, well, remember what you do, it's lambda 1, lambda 2, so it would be 1, 2. Kind of strange, right? It's odd. Why would you ever do this? It seems completely crazy. Why would you choose a different basis than the standard basis? I promise you there are very good reasons, especially when we come to think about linear transformations. So looking at this, I mean, we see a little bit of a, it's not really a coincidence, but it's something worth pointing out. You see this here? This is exactly the vector we're interested in. That 1, 2 there is precisely 5, 3 written in B coordinates. So that's part of a more general thing, but maybe before I say kind of what the general principle is, there's an important way to kind of view this. So let me kind of just bring the following picture in. The way you should be thinking about this is the follows. I mean, at least in R2, if I choose a non-standard basis, so B1 and B2, that's going to give me some sort of warped grid of points if I'm talking about linear combinations of B1 and B2. So when you're talking about positions in a non-standard coordinate system, it's like you're choosing kind of a warped coordinate system. You're not just doing the usual kind of XY coordinates, you're kind of warping them in some way. But it's not completely crazy warping. It's just kind of parallelogram stacked together. So, for example, 5, 3 in this picture would be this green position, and it's 1, B1, and it's 2, B2s. So that's the reason it's positioned, well, it's coordinate 1, 2, and B coordinates. So this general principle is kind of what's going on. If you're choosing a non-standard basis for R2 or R3 or Rn really, all you're doing is describing your positions in Rn, but using kind of a slightly warped coordinate system. Yeah, so that's the basic idea. So it seems strange. I know it's not obvious why you would do this, yet it'll be really important. So let's kind of capture this. So what happened here? How did I get 5, 3 written in B coordinates? Well, I took this augmented matrix and I solved it, and at the end I got the coordinates there. So this general principle always holds. It's a really useful fact. So the general situation here at least in Rn is the following. If you have, again, I'll write it again, if I have B is equal to B1 to Bn, a basis for Rn, then this implies, well, to find the coordinates of an x, all you have to do is write down the following augmented matrix. You write down your basis, and you write down your x that you want in coordinates. Then what do? You do row operations. To put it in reduced echelon form. If you think about it, when you put it in reduced echelon form, what are you going to end up with? Well, B1 to Bn are n vectors in Rn, so it's kind of a square matrix. They're all linearly independent, so putting it in reduced echelon form will give you the identity matrix here, just like we saw above. And what are you left with? Well, here you're left with x written in B coordinates. So this is a pretty slick way to work out what something in Rn is, at least written in coordinates. This doesn't work if you're not in Rn, because if you're not in Rn, I mean, B1 to x, they're not coordinate vectors, or they're not column vectors. So this only works for things in Rn. Okay, so an important thing about this is the following. I think this is kind of the most important observation here. The key observation is, well, what is the process of taking coordinates? I mean, choosing a basis. B as above for a vector space V. So we go back to the general case for a vector space V. It allows us to identify V with Rn. And that identification is like a function if you want. So I could write it like this. This process of taking coordinates, to any element in V, I associate to it what? Well, it's going to B coordinates. So that's an element of Rn. So x here has corresponding to it x written in B coordinates. So a few things to be said about this. V is a vector space, Rn is a vector space. It turns out, a little bit of work, this is linear. So there's a linear map between the two of them, so it preserves addition and it preserves scalar multiplication. That's really good. In addition, it's onto, because every single coordinate corresponds to a vector, and it's one-to-one, essentially because of the linear independence of the basis. So this is a one-to-one onto map which is linear, and a one-to-one onto map is one which essentially is a perfect matching up of the elements in the domain and codomain. So really intuitively what this is saying is the moment I choose a basis, this gives me a perfect matching up between the vector spaces V and R in a way which preserves the addition and preserves the scalar multiplication. So essentially their structure as vector spaces is the same. They may look different, but if I'm only asking questions about addition and scalar multiplication, answers on both sides will be exactly the same. Maybe I should say the way that things match up here is quite nice. If I take, say, BI, what's the coordinate of BI? Well, it would be 0, B1, some ... until you get to BI, and then some zeros again until you get to Bn. So what does that mean? Well, that means that if I take BI, I write it in B coordinates, it's 0 and then 1 at the ith place and then 0 from then on, so it's just EI. So what's really going on here is the following. Your basis on the V side is matching up with a standard basis. It's really neat. So the moment you choose a basis for V, this coordinate thing allows you to match up your vector space V with Rn in a way that matches the basis with the standard basis. So it's a really nice idea. So this is an important way. This is how you should really thinking about this. The moment you choose a basis, you can convert everything to kind of B coordinates, and that gives you an identification with Rn. But the linearity is really what saves things here, or makes things really important. So structural properties. structural properties and vector calculations. Let me write this properly. Vector calculations are preserved when switching from V to Rn. Now, why is that important? Well, it means I could have a collection of vectors in V, quite abstract, and I maybe ask, are they linearly independent or are they spanning? And if I choose a basis, I can convert them to vectors in Rn, and then any question about them I have in V, I can convert to a question in R. If it's true or false there, it's true or false in V. So let me give you an example to illustrate the power of this. So here's a question for you. Is the set of polynomials, we'll say x squared, I don't know, plus 2x plus 1, x squared, x plus 1, linearly independent in, let's say, P2R? That's a great question. So I could write down the definition directly, linear combination equal to 0, and kind of go through kind of the usual algebra to find that all the coefficients are 0. So this is the question. But notice I can match these up. So if I was going to use the standard basis for P2R, these vectors, there you go, let's copy it. These vectors will match up with what? They'll match up with the vectors, what would it be? It would be 1, 2, 1, 0, 0, 1, and 1, 1, 0. They would match up with those vectors. And this is standard basis coordinates. And the standard basis is a really nice matching up. So what do I know? Well, any question I ask about the original, I convert that to a question about the vectors in R3 now. Remember, P2R is three-dimensional. So some row reduction implies that this set, so I can now use my tools from kind of the Rn case, it's really great. This thing is linearly independent. So I'm not going to go through that procedure. You put them in a basis, you do row reduction, blah, blah, blah. There's a pivot in every column. These are linearly independent in R3 though. But structural properties are preserved when switching from P2R to R3. So what does this imply? This implies my original collection of vectors these guys are linearly independent in P2R. So this is a very powerful approach. It means an abstract question in a difficult to get your hands on vector space. If I choose a basis, I can convert everything to questions in Rn, or I can hit everything with all of my tools of row reduction and that kind of thing. So this is the reason we looked at Rn in so much detail. It's because we want this kind of abstract theory, but we also want to be able to kind of do calculations in it. And to do calculations in the abstract world, a really powerful technique is to choose a basis and then convert to Rn and go through the procedures there. So this is pretty great. This means that all of this abstraction can ultimately be related back to Rn if we want to do calculations. So there's a bit of an issue with this. It's a real subtlety which causes a lot of confusion. This is a warning, I think. So different bases. So remember, there are many different bases for a vector space. There's no one choice. Different bases will give different coordinate systems. Just think back to that R2 case. So I chose the basis 1, 1, 1 and 2, 1. That gave me a very different coordinate system than if I chose the standard basis. So this is pretty confusing. This means if I choose two different bases, I get two different coordinate systems. So let me just do a quick example. Yeah, let's do the following. I'll do one kind of exactly like I did before. So let's do V as R2. This is a good place to test stuff because it's quite easy to do calculations. And let's choose b is equal to, well, I'll choose the same basis I chose before, 1, 1. And we'll do 2, 1. And we'll do c, another basis. I'll do something a bit nastier, minus 1, minus 6, minus 1, minus 2. Okay, and now let's imagine writing, let's say, 3, 2 in b coordinates, and let's try also writing 3, 2 in c coordinates. So what do I need to do? Well, the usual business, I would go through row reduction on an augmented matrix, appropriately chosen. So if I do row reduction on this, what do I get? I'm going to get 1, 0, 0, 1, 1, 1. So remember what that means? This is going to imply that 3, 2, written in b coordinates, is 1, 1. It's not so hard to see. If I add 1, 1 to 2, 1, I get 3, 2. Let's do it in the other one. 1, 1, 2, 1. Ooh, okay, no, sorry, I'm doing the wrong thing. I want to do it on a different basis. So let's do minus 1, minus 6, minus 1, minus 2. That is a basis for sure because they're linearly independent, but we'll do 3, 2 again. So if I do row reduction, eventually I come to the following thing, 1 minus 4. So that implies, written in b coordinates, written in c coordinates, it's totally different. It's 1 minus 4. So different choices of coordinates, or different choices of bases, will give different coordinate systems. And the real problem is, I mean, in Rn it's not so bad because there's kind of this standout basis, the standard basis, we can kind of always use that. But in more general vector spaces, maybe there's no standout basis. Maybe there's no obvious one to choose. So this is kind of a defect in this. It really depends on my choice of coordinates. Some coordinates may give properties kind of, they may become more transparent. So here's the question. How can we switch between coordinate systems? It's quite a delicate question. So let's kind of think carefully about what's going on here. So let's fix two bases. B is B1 to Bn, let's say. And again, we'll do C is equal to C1 to Cn. Bases for some vector space V. So let's kind of draw what all this means. So if I've got two different coordinate systems, that means the following thing. I'm going to have two different identifications with Rn, aren't I? So this is one is going to be in B coordinates. The other one is going to be in C coordinates. And they're going to be different. Ooh, sorry, not R2, Rn. So let's think about this. If I take some x here, what's happening? Well, if I go down here, I'm going to get kind of x written in B coordinates. And if I go down here, I'm going to get x written in C coordinates. So the question is, how do I switch? How do I go from there between these two? That's the real question. How do I go between the two? So that should correspond, I think, to some function. There is some function which is going to go from, so maybe I should move this a little bit. Should I? Do I have enough space? Oh, I don't know. So let's move this up a little bit. So what's really going on is I want to come up with some way of switching from Rn in the B coordinates to Rn in the C coordinates. So that means I'm looking for some function from Rn to Rn which switches from x in B coordinates to x in C coordinates. So what we need is we need some function t such that if I take something written in B coordinates, it spits out the same thing but written in C coordinates. And this has to be true for all x in V. I should maybe first say that such a function definitely exists. Why? Well, when I go to B coordinates, remember this map here, It's 1 to 1 and onto. That means it has an inverse. So I can always go from one side to the other, but I've got to go in kind of a nasty way. I've got to kind of go backwards here and then down here. So this t does mean something. It is meaningful. The problem is that's super duper abstract and it's not very useful. So let's think a few things through. Let me maybe just gather a few facts for you. So the main fact is this map T is actually linear. That's very important. So that means this switch of coordinates I'm looking for is a linear transformation from Rn to Rn. So if it's linear, that means it's given by a matrix. So that means there is some matrix such that if I feed in B coordinates, I should get C coordinates out. And what is A? Well, A will be the standard matrix of T. So we've got to work out the standard matrix of T. So how do we work out the standard matrix of a linear transformation? Well, we feed in the standard basis, and those are the columns. So let's just recall the following. Saw this a moment ago, but EI is equal to BI written in B coordinates. Okay, so let's just go back up to here. Where am I? This here. BI, when I write it in B coordinates, is just the standard basis. That's the identification. It matches the basis to the standard basis. So what does that mean? Well, this has a very pleasant consequence that if I evaluate T at EI, it's equal to what? T of BI in B coordinates. But what's that? Well, the job of T is to switch from B coordinates to C coordinates. So this has to be equal to BI written in C coordinates. So this is kind of curious. So I think the following is the case. So yeah, so this is, maybe we're saying in words, this is vector BI written in C coordinates. So definition. These are going to be the columns of my standard basis. So the standard matrix. I'm going to give the standard matrix a name. So standard matrix I'm going to write as capital P, and then this weird notation with a C arrow in that direction, B. So this is the n by n matrix, which is, first column is B1 written in C coordinates, next column is B2 written in C coordinates, dot, 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 all the way along. So this is what B n written in C coordinates all the way down. So first of all, just to sanity check, this is n vectors. Everything's n. This is an n by n matrix. It's got a name. It's called the change of coordinate matrix. From what? From B to C. Why is it called that? Well, its job is to switch from B coordinates to C coordinates. So the key property of this matrix is the following. If I multiply any x in my V written in B coordinates by this matrix, I get x written in C coordinates. And this is for all x in V. So how do I actually work this out? Well, it's actually nothing like as bad as it might seem. So let me do it, at least in the kind of Rn case. So here's a general change of basis in Rn. So let's just remind ourselves, if I want to write something in certain coordinates, I have an augmented matrix that I need to kind of reduce. So if I want to write, say, BI in C coordinates, what would I do? I write down BI at the end here, CIs, and then I would do row reduction, just like we saw before, until I got the identity matrix on this side, and what I'd be left with here would be BI written in C coordinates. So how do I do that all at once? Well, that's the ith column now. That's the ith column of my change of basis matrix. So this implies, well, let's do kind of a super augmented matrix if you want, Cn, and then over here, instead of just BI, let's do all of them. Let's do B1 dot 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 to Bn. So if I do row operations on this, what am I going to get? I'm going to get, well, eventually the identity here. And then what am I left with? Well, the first column would be B1 written in C coordinates, then B2 written in C coordinates all the way along. What's that? That's exactly PC arrow B. So this gives an excellent algorithm for calculating the change of basis matrix. It's very similar to the calculation of an inverse matrix, but you're doing something completely different when it comes down to it. So let's do an example. Let's make sure this works in the case I did before. So let's have V is equal to R2. B is equal to, we'll do 1, 1. 1, 1. 2, 1. And C is equal to, well, the same basis I did before, minus 1, minus 6. Minus 1 is at minus 2. Okay, so imagine trying to work this matrix out. So what would I have to do? I would have to do the following thing. I would have minus, so I'd need to write C on this side, so minus 1, minus 1, minus 6, minus 2, 1, 2, 1, 1. So then I've got to go through the process of doing echelon form in this. So I'll go through this one really carefully. It's not so bad, it's the usual procedure. So first of all, I don't know, what should I do? Let's scale the first row, so it's 1s there. So it's multiplying by minus 1. In fact, let's scale the whole thing, so it looks like that. It's going to make my life a little bit easier. So 6, 2, minus 1, minus 2, minus 1, minus 1. Okay, so next, let's put it in, let's put this guy in echelon form. So let's take away 6 of the top, so that's going to be 0, minus 6, minus 4. So 6, I think I'm going to get a 5 here. Then 6, am I going to get 11 here? I'm taking away, so I'm adding 12. Is that correct? Hopefully. So then what am I going to do? I've got to scale now. So let's scale this guy by, let's scale this by minus 4. So I'm going to divide through by minus 4. I'm going to get a 1 there. So this is going to be minus 5 over 4, minus 11 over 4. Then what have I got to do? Well, I've got to get rid of that 1 above. So I'm going to take away the second from the first. So what does that give? 0. Oh God, so what is it going to be? It's going to be a minus 1 minus a fifth, so that's going to be a quarter. Oh God, then what is it? Minus 2 minus 11 over 4. I think that's 3 over 4. Okay, so this implies P, let's see, is equal to the matrix. It's not the nicest, it's a quarter, it's 3 quarters, minus 5 over 4, minus 11 over 4. Let's check this actually works. So let's take the vector, was it 3, 2 I did before? Yeah, so let's do a quarter. 3 over 4, minus 5 over 4, minus 11 over 4. Okay, so what was it written in B coordinates? So let's go back. In B coordinates, where are we? All the way back here. So in B coordinates, in fact, what am I going to do? Yeah, in B coordinates, so was it 5, 3, was 1, 2. So let's get this correct. So 1, 2. So this was, gotta hope this is right, this is 5, 3, written in B coordinates. So this, of course, is P. PC goes to B. So what this should be equal to is, well, it should be 5, 3 written in C coordinates. So what was 5, 3 written in C? In fact, wait a minute, I got the wrong thing. It was 3, 2 that I did. Wait a moment. Yeah, I'm looking at totally the wrong thing. Yeah, we should do 3, 2, not 5, 3. Because that's what we did with two coordinate systems. So 1, 1, this was 3, 2. So well, what I hope to get out? Well, I hope to get out 3, 2 written in C coordinates. So let's see what happens. This is going to be equal to a quarter plus a third, 3/4. Is that right? And then it's minus 5/4 minus 11/4. That's equal to what? 1 minus 4. Thank goodness that's equal to 3, 2, written in C coordinates, as we saw last time. So this is a pretty awesome way to switch between coordinate systems. It is quite time consuming to do. And this procedure only really works for Rn. Okay, so if I'm choosing different coordinate systems in Rn, it's a good way to switch between